Alright, good morning, or good afternoon, or good evening, whichever the case may be. In this video, we are going to be looking at, I'll show you the document real quick. This document here and filling this out. What is this document? Well, on your Blackboard page, if you go to Course Documents, and this is for the 014 section, if you're in the evening section, it's still found in the Course Documents, so the page looks different. Go into Course Documents. We're here in Unit 1, Chapter 8 on acids and bases. If we click on that, what I'm calling here Chapter 8 notes. This now says here Chapter 10, but it's still pH and buffers and acids and bases and whatnot. This document, if you click on this, document will open. It's a PDF file, right? I'm going to use this PDF reader down here to access it. And what this document is essentially a review page. So instead of going over this in class, I'm going to make these videos and you can access them and fill out this page yourself. The actual act of just listening to this video and writing this stuff down should help solidify some of the concepts that we've talked about in class. Then you should have a review sheet that essentially contains most of the information you'll need for the test on this unit. This is by no means replacement for the regular lecture. I still expect you to come to the lectures. In addition, when I'm filling this out, I'm not going to be explaining these concepts in nearly as much detail as I would in lecture. There are some concepts that I discuss in lecture that are not on here. This is not intended to be homework. It's not for, well, I should say, yeah, you're going to be doing this at home, or maybe at least outside of class, maybe at school or wherever there's a computer you can use. It's not intended for you to do on your own. It's intended for you to follow along this lecture and fill in these blanks and so forth. And it's not for credit. It's not assigned homework. First thing we have here is definition of acids. Now in the lecture I talked about some of the general concepts or generalities of acids and bases. Here we're just talking about the Arrhenius and Bronsted-Lowry definitions. Okay, so an Arrhenius acid is a compound, right? So we can say it's a compound that contains a hydrogen ion, or if you wish, it's a compound that dissolves. And we've only talked about water as a solvent, so it dissolves in water, dissolves to produce hydrogen ions. An Arrhenius base is a compound that contains the hydroxide ion, or if you wish, dissolves to produce hydroxide ions. So I'll try to use red for acid, blue for base, and be consistent with it. But if you remember, acids turn litmus red, and bases turn litmus blue. If we complete these following reactions, HCl is an acid. Oops, use red for. Actually, use black for that. This should be a lowercase l. HCl is an Arrhenius acid. It has a hydrogen ion, and when it dissolves, we produce hydrogen ions and chloride ions. Sodium hydroxide, NaOH, is a base, contains a hydroxide ion. When it dissolves, we get sodium ions and hydroxide ions. So that is how Arrhenius would envision acid-base character. It's a little bit different from what Bronsted and Lowry consider. So let's scroll down here. Alright, so Bronsted. What did Bronsted say about acids? Bronsted acid is a proton donor. If you remember, a proton in solution is really the same thing as a hydrogen ion. So a proton or hydrogen ion donor, and a base is a proton or hydrogen ion acceptor. In the reactions below, you notice water is now a reactant. It's not just on the reaction arrow. As a solvent, it's actually a reactant. HCl is still an acid, and as an acid, it's going to donate its proton to water. There's an unshared pair of electrons on water, and the Lewis structure of water has these unshared pair of electrons. These non-bonding electrons are often also referred to as lone pair electrons. They accept the hydrogen, so what do we end up with? Well, we end up with the chloride ion, right, because it lost its hydrogen, and water, which was H2O, becomes H3O+. H3O+ is known as the hydronium ion, and it is functionally equivalent to a hydrogen ion that's dissolved in water, so it's aqueous, which is also the same thing as a proton that's dissolved in water, or is aqueous. Okay. Ammonia is a base. Ammonia also has an unshared pair of electrons. In this case, water is acting like the acid, and it's donating its hydrogen ion. I'll put a little hydrogen ion here. Right. So water is donating its hydrogen ion to ammonia. Ammonia then goes from NH3 to NH4. It has a +1 charge, and what's left of the water after it loses one hydrogen is the hydroxide ion. Right. So this is the ammonium ion. Alright, number 3 here, they start talking about acid-base conjugates. Now, acid-base conjugates are a feature of the Bronsted-Lowry definition only. So we talk about Bronsted-Lowry acid-base conjugates, not Arrhenius acid-base conjugates. But I should point out that Arrhenius acids and Bronsted-Lowry acids, those two definitions are consistent with one another. So here we're using HCl as a Bronsted acid, but clearly it's also an Arrhenius acid, except that instead of producing hydrogen ions, we say, well, it produces this hydronium ion. Again, the hydronium ion really is functionally equivalent to a hydrogen ion that's dissolved in water. Similarly, ammonia here is a Bronsted base because it's accepting a hydrogen ion. That makes water the acid. Water is donating the hydrogen ion. But when we dissolve ammonia, which it turns out it's a gas at room temperature, when we dissolve it in water, and you can have gases dissolved in water if you're drinking a soda while you're watching this, those bubbles in there are carbon dioxide gas that are dissolved in the soda, dissolved in the water, and they're coming out of solution. But this gas, ammonia, is dissolved in water, and when it does so, it reacts with some of the water molecules and produces hydroxide ions. So according to Arrhenius, this would also be a base because it dissolves in water to produce hydroxide ions over here. The only difference is the hydroxide ion is not present in the NH3. It actually comes from the water. But sometimes you'll see, and I'll just write this here, ammonia that's dissolved in water, sometimes you'll see it written as ammonium hydroxide. And as I pointed out in lecture, ammonium hydroxide, this compound here, is really a bit of a misnomer because it doesn't exist really. What you have here is a solution that contains ammonium ions and hydroxide ions, but there is no ionic compound ammonium hydroxide. You can't get a sample of just pure ammonium hydroxide like you can, say, with sodium hydroxide. Sodium hydroxide is a white crystalline solid. You can hold it in your hand. Sodium hydroxide is a white crystalline solid. Well, I wouldn't recommend holding it in your hand, but you could hold it in a weighing dish or something. But ammonium hydroxide doesn't really exist. Nevertheless, sometimes you'll see this kind of nomenclature. All right. So then they start talking about acid-base conjugates here. The thing about acid-base conjugates is they differ by a single hydrogen ion. In the reactions up above here in number 2, acid-base conjugates appear on opposite sides of this reaction arrow. So one's a reactant, one's a product. I'll just say opposite sides of the reaction arrow. We have reactants on one side, products on the other. An acid will, well, let's see here. The acid, HCl, clearly an acid. Its conjugate base is not water. Its conjugate base is on the opposite side of the reaction arrow. It's the chloride ion, because the chloride ion differs from HCl by a single hydrogen. So I would just connect these two thusly. These guys are conjugates, or acid-base pairs. You can think of them as pairs if you wish. Kind of go together. Water is a Bronsted base in this case. It's accepting the hydrogen from HCl. So water is the base in the reactant side. On the right-hand side, we see the hydronium ion, H2O, H3O. They differ by a single hydrogen. They're on opposite sides of the reaction arrow. And so here's our other acid. Oops, I want to black for that. Here's our other acid-base conjugate. It's water and the hydronium ion. The next reaction down here for ammonia, we said ammonia is a base. It's accepting the hydrogen ion from water, so water is the acid. It's donating its hydrogen ion. On the product side, we see NH4. It's got one more hydrogen than NH3. So these guys are acid-base conjugates. Ammonium is the conjugate acid of ammonia. Right, so here's the base, here's its conjugate acid. Similarly, water is the acid, and I'm going to use red here so we can distinguish it. Here's its conjugate base, the hydroxide ion. They differ from a single hydrogen. They're on opposite sides of this reaction arrow. Okay, so water in this reaction is an acid, the hydroxide ion, of course, the quintessential base. Okay, so there should be a list of acids and bases in your textbook. I'm not sure what page it's on, but these are the ones that I want you to know, and you should know the names and the formulas for all of these acids and bases. Okay, so there's actually, I'm sure the book probably gives you a more elaborate list, but the acids, we have hydrochloric, H3PO4 is phosphoric. Phosphoric acid is found in colas, for example. One of the properties of acids that I talked about is acids have a sour taste, or they're tart, and phosphoric acid is used in sodas to impart that kind of tanginess, that tart flavor. So I should say acid, right? Hydrochloric acid, phosphoric acid. HNO3 is nitric acid. H2SO4 is sulfuric acid. Sulfuric acid. Sulfuric acid is battery acid. It's the acid that you find in automobile or car batteries. CH3COOH, this is acetic acid. This is the active ingredient in a vinegar. Notice the spelling, it's acetic acid, not acidic, but acetic acid. The term acetic comes from the Latin acetum, which means sour. And if you've ever, I'm sure you have tasted vinegar before, it is sour. H2CO3, this is carbonic acid. Carbonic acid is also present in sodas, and this acid is formed when carbon dioxide gas dissolves in water. So this is carbonic acid. Okay. I'm not going to bother writing the names for these guys, but sodium hydroxide, potassium hydroxide, and again I've mentioned ammonia or ammonium hydroxide. Right. Now, I also ask you to know whether they're strong or weak. What does strong mean? Well, strong acids dissociate 100%. Dissociate 100%. And weak acids less than 100%. So in addition to knowing the names and formulas for these acids, you should be able to classify them as strong or weak. Turns out there are many more weak acids than strong acids, so I'm just going to tell you which ones are strong and the other ones are weak. So HCl is strong, as is, and I think I mentioned this in class, hydrobromic and hydroiodic are also strong. Okay, nitric is a strong acid, sulfuric acid is a strong acid. The weak acids, phosphoric acid is weak, acetic acid is weak, carbonic acid is weak, and another one they don't have on here is hydrofluoric acid. It's also weak. No, there's just 5 strong acids. Just know these 5, and if it's not hydrochloric, hydrobromic, hydroiodic, nitric, or sulfuric acid, then it's weak. As I said before, there are many more weak acids. I'm not going to list them all, but we have a whole chapter on carboxylic acids later in the semester, and those are all weak acids. So know the strong ones, and if it's not on that list of strong, hence it's weak. As far as bases go, the only thing you have to remember here, at least for now, this is the only weak acid that we're going to be dealing with in this unit or this chapter. All other bases are considered strong. Describe the strengths of acids and bases in a qualitative way, i.e. no equations. So the ionization constant, Ka of a weak acid, actually let me find a little bit more room here. So I'm going to draw the general acid dissociation reaction. Okay, so HA is the acid. You react that with water in a Bronsted-Lowry sense, and you get the conjugate base A minus plus the hydronium ion H3O plus. All right, the Ka is this equilibrium constant, and it is really nothing more than a ratio of the products here on the right hand side over the reactants. We're going to leave out the concentration of water. You can look back in your lecture notes and figure out why that is. But essentially, this is a ratio of the products over the reactants. So it will take the form of like this, the conjugate base concentration times the hydronium ion concentration divided by what we call the free acid HA concentration. Okay? The ionization constant Ka of a weak acid, HA, is, and that's this thing here. Right? It's this ratio of concentrations, products over reactants. Okay? The ionization constant of a weak acid then is going to be a small number. Generally on the order of 10 to the negative third or less. Okay. Similarly, the ionization constant of a weak base is a small number. We didn't really talk about weak bases in the lecture. I'll go ahead and draw or write the equilibrium expression for a weak base. Actually, let me write the reaction down here. I think I did do this in class, but I don't know if I wrote down the equilibrium expression. All right, so here's our base with its unshared pair of electrons. That's what makes these things Bronsted bases. It's going to accept a hydrogen from water, so we get BH plus. That's our conjugate acid. The conjugate acid of base B is BH plus, and OH minus. So the Kb here, again, it's just simply a ratio of products over reactants. We're going to ignore the concentration of water in this case. So it's simply the concentration of BH plus, that conjugate acid, times the concentration of the hydroxide ion, divided by the concentration of the free base. Like that. So it has a similar form, except instead, with the Ka we have the conjugate base up here, and the hydrogen or hydronium ion. For the bases, we have the conjugate acid and the hydroxide ion. Right. The stronger the acid, the larger the Ka. Wait for that. The larger the Ka. If you think about it, Ka is products over reactants. So a strong acid, what does that mean? It means it dissociates, closer to 100%, which means the equilibrium lies farther over to the right. So we could have equilibrium arrows like this, indicating that the reaction is favoring products. Okay. The weaker the base, the smaller the Kb. And we could draw equilibrium arrows. So in this case, it would favor reactants. Like that. So the smaller the base, the smaller the the weaker the base, the smaller the Kb. If it's a weak base, right, we don't have a, down here, here's our base reaction. If it's the weaker the base, it means we don't produce as much of these products. So if we look at the equilibrium expression up here, we don't have as much in the numerator, much of these products. We've got a larger number down here. A small number divided by a larger number, right, gives us a small number. Just like weak acids have small Kas, so do weak bases. They have a small Kb. The pKa of the acid is simply the negative log of the Ka. And when you think, remember, when you think of logs, think of exponents. The pKb of a weak base is simply the negative log of the Kb. This comes into play when we start talking about buffers and using the Henderson-Hasselbalch equation. One thing to keep in mind is the weaker the acid, turns out it's the larger the pKa. The larger the pKa. So these if you look up here, stronger acids have a larger Ka. Weaker acids, opposite, stronger versus weaker. Weaker acids have a larger pKa. Or if the other way to think of it, the stronger the acid, the smaller the pKa. So they're kind of opposites, the Ka and the pKa in that sense. And the reason for that is this negative sign. Right? It's not just a log, it's a negative log. So if we had a Ka on the order of 10 to the negative fifth, right, pKa isn't negative 5, but the opposite, or the negative of a negative 5, so it's a positive 5. One way to keep this straight is remember pH, the pH scale. pH, we have low values of pH, less than 7 are acidic. All right? So one way to think about pKa's is with regard to that pH scale. So the weaker the acid, you can think of it as the more basic pKa. So just as a basic pKa would be above 7, you could have, say, a pKa of 10. That would mean it's a weaker acid. A stronger acid, the more acidic the pKa. Just as a more acidic pH would have a lower value, say an acidic pH is a pH of 2, a stronger acid would have a smaller pKa, like a pKa of 2. So if you wish, you can think of it this way, as Ka's increase, right? This means stronger acid. The pKa's decrease also means stronger. And of course, the opposite is true for if we went the other way, for weaker. Write equations that illustrate the stepwise dissociation and reaction of polyprotic acid. So polyprotic, what does that mean? Well, a monoprotic acid would be something like HCl down here. It just has one proton, mono for one. A diprotic acid would have two. Phosphoric acid has three. There's three hydrogens. So it's a triprotic or polyprotic acid. So it's a triprotic or poly more than one, or a polyprotic acid. And the thing about phosphoric acid, when it dissolves, it doesn't. Give you an example. If we had something like, say, aluminum chloride, and we dissolved aluminum chloride is a solid, say we dissolve it in water. Okay, now this aluminum chloride is a salt, it's not an acid, but we'd get the aluminum ion and three chlorides, right? Because there are three chlorides in this formula. It dissociates 100% all at once. Weak acids that, I should say any acid really that does this, even if it's a strong acid like sulfuric acid. Sulfuric acid has two hydrogens. It doesn't deliver all three hydrogens at once. Instead, it will deliver one hydrogen. Okay, so it went from H3PO4, it lost a hydrogen, now it's just H2PO4. It's going to have a minus charge. H2PO4 still has two hydrogens, so it's still an acid, and it can deliver another hydrogen like that. So it went from H2 now to HPO4. It's going to have a minus 2 charge. This still has one hydrogen left, so we can deliver one more hydrogen and end up with PO4 minus 3. So each of these reactions, now phosphoric acid is a weak acid, so there are Kas for each of these reactions. Each hydrogen that comes off has its own Ka, so I just call this Ka1, Ka2, Ka3. They all have their own value, and we could talk more about the relationship between those values and whatnot, but I just want you to understand that phosphoric acid, sulfuric acid does a similar sort of thing. It does not deliver all three hydrogens at once, unlike a salt would, like this aluminum chloride. All three chlorides come off at once. It's just one reaction. This is a stepwise approach. Okay. All right, salts. An acid and a base react to form a salt and water. This is a neutralization or a double displacement reaction. Here we're going to just switch out the sodium and the hydrogen. They'll switch places. Right. So the sodium combines with the chloride. We get the salt. In this case, it's table salt. And we get HOH, which we refer to as water. Right. It's not hydrogen hydroxide, it's water. Right. This is a neutralization reaction. The reactants are an acid and a base. And the products are a salt and water. Do calculations involving the pH concept. pH is nothing more than mathematical representation of the hydrogen ion, or if you wish, hydronium ion concentration. Right? The H in pH stands for hydrogen, and the equation simply pH equals the negative log of this hydrogen ion concentration. Oh, you know, one thing I didn't mention in lecture, we do discuss this in lab. pH can be measured using a pH meter. Actually, I did talk about that. A pH meter or pH paper. Okay. pH is not measured using litmus paper. The difference between pH paper and litmus paper: litmus paper has only one acid-base indicator in it, and it turns red in acid and base in blue. So litmus paper only tells you if it's acidic or basic. It doesn't actually tell you what the value of the pH is. pH paper, you'll be using this in lab, pH paper has a number of different acid-base indicators soaked into that paper, and so there's more than just two color changes, and based upon this great gradient of color changes, you're able to estimate what the pH is. Similarly, if you've done titrations before, acid-base titrations do not tell you what the pH is. However, they do tell you what the acid concentration is. So whereas the pH gives you an indication of how much hydrogen ion is present, a titration tells you how much of the acid is present. As I mentioned in class, when you stick a pH meter into a solution, it is measuring this hydrogen ion. Right? So here's the meter. It's measuring the concentration of hydrogen ion. A titration measures the amount of acid. Those are not the same thing. Okay, complete the following table. I'm going to go through this pretty quickly. We did this in class. So pH is a negative log of the hydrogen ion concentration. So when you think of pH, think of exponents. So the exponent here is 10 to the negative 7. This is a molar concentration. A couple equations you should remember, right? pH plus POH equals 14. And then we also had, I'll put it here, the Kw, which is 10 to the negative 14, equals hydrogen ion concentration times the hydroxide ion concentration. So two equations you need to know in order to fill out this table. So the pH is 7. The POH, 7 plus 7 is 14, right? That means the hydroxide ion concentration has a value of 10 to the negative 7 molar as well. And this is a neutral solution. If the pH is 10 to the negative 2, sorry, the pH, the hydrogen ion concentration is 10 to the negative 2, the pH is 2, right? The negative of this exponent. If the pH is 2, the POH must be 12. 12 and 2 is 14. And so the hydrogen ion concentration is 10 to the negative 12. Similarly, if the POH is 2, the pH has got to be 12. Right? pH is 12. That means the hydrogen ion concentration is 10 to the negative 12, and the hydroxide is 10 to the negative 2. One thing I caution students, if you're given a concentration like this, hydrogen ion concentration 10 to the negative 2 molar, go ahead and convert that to a pH. And then once you know what the pH is, then decide if it's acidic, basic, or neutral. The value of 2 here, right, the negative of this exponent, is less than 7. It tells us this solution is acidic. Here the value 12, right, they're given the POH. We know that the 2 plus 12 has got to equal 14, right? So pH is 12, this is basic. And lastly, if the hydroxide ion concentration is 10 to the negative 11, the POH is 11. What is a pH? Well, 3 plus 11 is 14. 3 is less than 7, so this is acidic. And the hydrogen ion concentration is 10 to the negative 3. Right, earlier we were talking about salts. Right, a salt is formed from an acid-base reaction. Right, so let's just say we have HCl plus NaOH. That gives us NaCl plus water. Right. So it says explain or write illustrations that reactions that illustrate this hydrolysis. Hydro is water, lysis is splitting apart. So what we're talking about is when a salt like this goes into water, you dissolve this in water, what happens? Does the pH go up? Does it go down or stay the same? In other words, what we're asking is hydrolysis. We're asking, is the salt acidic, basic, or neutral? Is it an acidic salt, basic salt, or neutral salt? Acidic, basic, or neutral. Okay. So I think I have these this table here reversed from how I had it in my notes, but that shouldn't matter. We'll use an example of a strong acid. We'll use HCl. A weak acid, we'll use hydrofluoric acid. For our bases, a strong base, we'll use sodium hydroxide. For the weak base, we can use ammonia, or if you wish, ammonium hydroxide. Same thing. Okay. If you have a strong acid, strong base, these guys neutralize one another, of course, but they fight to a draw. So the salt we get, sodium chloride, is going to be neutral salt, neither acidic nor basic. If we have a strong base but a weak acid, the strong base beats up on this weak acid, and we get a basic salt. So the salt here is sodium fluoride. This would be basic. So if I say, okay, what's the acid-base character of the salt, you can go through a number of steps. Let's just say here, sodium fluoride, acidic, basic, or neutral. How do you know? First thing, split it up into the ions. So you have to know, okay, sodium has got the positive ion, fluoride's got the negative ion. Second step, from the acid, no, the cation comes from the base. All right, so we'll add the hydroxide ion up here. Right. The anion comes from the acid. Right, so we'll add hydrogen ion here. So then the third step, you must ask yourself, is the acid strong or weak? Is the base, let's spell it out, strong or weak? Once you've done that, once you've identified the acid and base used to make that salt, you can tell if they're strong or weak, and you can plunk it into one of these 4 quadrants. Right? So the next quadrant here, we have a strong acid, HCl, and a weak base. The strong acid beats up that weak base. We're going to have an acidic salt. And the salt we get here is going to be ammonium chloride. The last quadrant here, where we have a weak base and a weak acid, the salt we're going to get is ammonium fluoride. And the pH, as I mentioned in class, this depends. And it depends upon the Ka versus the Kb. Because although they're both weak, one is going to be stronger than the other, so whichever value is larger, the Ka or the Kb. If the Ka is stronger, it's an acidic salt. If the Kb is stronger, it's a basic salt. If they happen to be the same, then it would be neutral. All right, explain and write equations that illustrate the action of buffers. Buffer is a mixture of a weak acid and its salt. The salt is really just a source of the conjugate base of that weak acid. Okay. The acid reservoir is the weak acid. The hydrogen ion sponge, the thing that's going to soak up those hydrogen ions, is the conjugate base. The weak acid here, the hydrogen ion reservoir, this weak acid is used to buffer against a rise in pH from the addition of hydroxide ions. So the weak acid buffers against addition of hydroxide ions. So it keeps pH from rising. Right, what do acids do? Acids lower pH, so that's what that does. It keeps pH from going up. The base is just the opposite. The hydrogen ion, or the acid sponge, is soaked up by the conjugate base. Right? This buffers against hydrogen ions and keeps the pH from falling. All right. You add acid, pH go down, but we've got this conjugate base to soak up those hydrogen ions and keep it from falling down. So the reaction, I think in class we used acetic acid, so here I will use carbonic acid. This is the other acid that you're going to be using in class, or in lab I should say. Okay, so I kind of drew it in an Arrhenius sense, but we'll be talking about it in a Bronsted-Lowry sense. I just didn't bother to put the water in here. So carbonic acid here is a weak acid, which means it's got, if we dissolve the stuff into water, most of it's going to dissolve like this. A little bit dissociates. So we have these hydrogen ions left in reserve. This is our hydrogen ion reserve, which means if we remove hydroxide ions, say by adding a base to form water, that would normally lower the pH if you add hydroxide ions. In other words, the hydrogen ion concentration would decrease, but instead what happens is these hydrogen ions in the carbonic acid replenishes those that are lost and keeps the pH constant. So this will pull the equilibrium over to the right. Okay. And in opposite fashion, if we add hydrogen ions, remember I used that YouTube analogy, and YouTube is not a video sharing website. The YouTube is a piece of glassware that looks like a U. The hydrogen ion here added to the right hand side forces the equilibrium back to the left. What allows us to do that is the fact that we have a bunch of this conjugate base. This is a conjugate base, and it soaks up hydrogen ions. Bases are proton acceptors. The bicarbonate ion here accepts the extra hydrogens and forms the carbonic acid. The source for this conjugate base is not here per se, but in a buffer. This comes from the salt. And in this case, maybe the salt is sodium bicarbonate or baking soda. Calculate buffers. Buffer pH using the Henderson-Hasselbalch equation. The pH of a buffer depends upon two things. It depends upon the pKa of the acid, that's kind of our starting point, and the ratio of the salt concentration over the acid concentration. If you look at the Henderson-Hasselbalch equation down here, the pH equals to pKa plus not just this ratio, but the log of this ratio, the salt over the acid. And as mentioned in class, buffers are most effective when the pH of that buffer equals the pKa of the acid. What that means is the salt concentration equals the acid concentration. Right? So this ratio of salt over the acid is 1. And if we look at this Henderson-Hasselbalch equation, when this ratio is 1, the log of 1 is 0. This log term falls out, and pH simply equals pKa. Okay. Number 12, some other terms you should know. This should be hydroxide, not hydroxyl. Hydroxide ion. Strong acids, weak acids, we've talked about weak bases. Hydronium ion, that's H3O+. Okay. And I know we've talked about other things in lecture. This doesn't include everything, but it does go over quite a bit of what we talked about in lecture. This last part here says study page, health note, page 405. This is not found in your book, and I will talk about this, but that will be in a different video, and it will not be on the test. It might be as extra credit, but we didn't go over this at all in lectures, so I'm not going to put this on the test for credit. There's no homework assignment for this, but I do plan on producing another video that talks about the respiratory control of blood pH and this blood buffer, this carbon dioxide, carbonic acid, acid-base buffer. But that'll come in another video.